Okay, today I want to take a little time to discuss some more about some discontinuities. Alright, if you are not familiar with the topic of discontinuities, alright, then you probably need to watch one of my other videos. I made another video where I talk about the different types of discontinuities, how you locate them on the graphs, what they look like, that sort of thing, and you really do need that background information before you watch this video. I'll go ahead and put a link for that video down in the description. So, prefacing that with that knowledge, then we ought to be able to address questions like this. Alright, let's suppose that they tell you to find the x values, if any, at which f is not continuous. Alright, and then they follow that up with which x values are removable, non-removable, if discontinuity exists. Alright, so we're just going to run through some examples on how you would go about approaching answering questions such as this. Alright, so in my first example right here, I've got f of x equals x squared plus 5x minus 1. Okay, so hopefully you recognize that right off the bat. That's a polynomial curve. Alright, it is an x squared, so it's going to be a parabola. Alright, and hopefully somewhere along the line you've been told that all polynomial curves of degree 2 or higher are smooth and continuous. Alright, so it's going to be continuous everywhere. Alright, so I don't have any discontinuities on here. So as an answer, you just might want to write something like f of x is continuous. Okay, because I don't have any discontinuities, so I don't have to worry about it. Okay, so f of x is continuous. Alright, taking a look at this example, f of x equals 1 over x squared plus 3. Alright, I do have my students memorize several basic graphs and how they shift and what they look like. This is not one that I really have them memorize, alright, but it is a relatively simple one. There's a variety of ways you can approach this. Alright, you could just take a look at this. Okay, it's a rational function. Alright, so things that you have to worry about are, is there any restrictions on this domain? Is there any number that I would plug in for x that would make me end up dividing by 0? That'd be a bad thing. That's going to create a problem for me here. Alright, but if you just start playing around with some numbers, if I plug in a negative, alright, negative anything, negative 1 squared is going to be 1. 1 plus 3 is going to give me a 4, so I'm going to be good there. If I plug in 0, alright, I'll have 3 in my denominator. If I plug in a positive number, like say if I plug in 5, that'd be 25 plus 3 more. I'm still going to get a real number on that. Alright, so I really don't have any restrictions on this whatsoever. If I have no restrictions on my domain or anything that's going to keep me from doing that, the function has to be continuous. Alright, so again, this turns out to be a continuous function, so I don't really have to worry about any discontinuities. Alright, f of x is continuous. If you weren't sure about that, or you couldn't go through that analysis to come to the conclusion that it is continuous, you could always use a graphing calculator and then put that in. Alright, now on this example here, we've got f of x equals sine pi over 2x. Okay, now hopefully you recall the sine graph is continuous everywhere. It's a nice little curvy line, curvy graph, and going left to right in all directions, both directions. Alright, and that little coefficient there, alright, it's just going to kind of play with the graph, compress, expand in one way or another. Okay, so I can conclude on this one that f of x is again continuous on the entire domain. So f of x is continuous. Alright, so I just wanted to throw those in there because even though they're asking you to identify discontinuities, they will give you functions which are continuous. Alright, you don't have to worry about them. Alright, now for the ones that there's a little bit more work to. Alright, let's take a look at this example. I've got f of x is equal to 2x over x squared minus 5x. Alright, so this again is not going to be real easy. I'm not going to be able to sketch it. I can't do a rough sketch really fast or anything. So I am going to want to take a look at, well, what's happening to my denominator? Do I have some restrictions that's going to be placed on this? Alright, so first thing I would probably do is look to see what I could factor. Alright, ultimately I'm going to see if there's things that I can cross out, things of that nature. Okay, so let's take this 2x over. Alright, now let's take that denominator and go ahead and factor it. If I factor out an x, I'm going to have an x minus 5 in my denominator. Alright, this is going to let me see my restrictions really easy here. Okay, now looking at this denominator as it's factored like this, alright, I've got some restrictions. If x is 0, alright, I'm going to have a 0 in that denominator. 0 times anything is going to be a 0. Alright, that's going to be bad. Okay, so right here I've got x cannot equal 0. That would be causing that division by 0. Okay, looking here, all right, I cannot let x equal 5 because if x is 5, again, I've got a 0 right there. All right, so yes, I know from doing this and seeing these restrictions in my denominator that the function is discontinuous. Okay, so here let's kind of write that out. Let's write it out as discontinuous. All right, it is discontinuous. All right, but why? All right, because there are restrictions for the denominator. All right, that's one way to put it. All right, now depending on how well you remember some of your pre-calc skills and everything, all right, that denominator right there, that's going to tell me where my vertical asymptotes are. So in a pre-calc class, you would take that rational function, you take that denominator, set it equal to 0, and solve just like I have done here. All right, and then whatever you get as your restrictions, if you take it and plug it into your numerator and it is a non-zero number, you know you've got a vertical asymptote going on. Okay, so this x equals 0, well, if I take that and plug it back into that numerator, I get 0. Okay, so I don't have a vertical asymptote there. All right, but obviously I've got something else going on there because I can't have x equals 0. All right. At x, you know, I said x can't be 5. All right, well, if I take 5, plug it back into that numerator, 2 times 5 is going to give me a 10. I'm good there. All right, so depending on how much you remember, all right, this clearly tells you that you've got a vertical asymptote at 5. Okay, and then the only other thing that could be going on here, all right, I cannot let x equal 0. All right, it's not going to be in the domain of my function, so there's going to have to be a hole there. I know it's not a vertical asymptote, so I'm going to have a hole there. All right, now let's show how it's a hole. All right, let's take that expression, that 2x over x minus 5. Okay, now if I take this expression and I simplify it, all right, what am I got? I got an x on top and I got an x on the bottom. All right, so I can cross them out, right? That's simplifying a rational expression. All right, or in other words, I am removing that x equals 0 right there. All right, so then that discontinuity is a removable discontinuity. I just removed it when I crossed it out. All right, and then a removable discontinuity is a hole. Okay, so let's kind of sum up what we've got here. All right, we know it's discontinuous because we got restrictions in that domain. All right, now it specifically wants to know which x values are removable, non-removable if a discontinuity exists. So I would probably sum up an answer as discontinuities. Or it's here, let's just say discontinuous. Didn't spell that right. Let's put a little u in there. Discontinuous at x equals 0, and we can conclude by crossing that out there that it is a removable discontinuity right there. And then my other one is at x equals 5. All right, and we concluded that it's a vertical asymptote going there, so I've got some type of infinite discontinuity going on, so that makes it non-removable. Okay, so answering the question right there. All right, so clearly way more work to the problem when you do run into the discontinuity occurring. Okay, now let's do a couple other examples where you've got a little bit more work to them and there are discontinuities that are showing up. Okay, so in this right here, I've got f of x equals x plus 2 all over x squared minus 4. Okay, so again, all right, you're not going to know what that sketch is right off the top of your head, and let's assume you don't have a graphing calculator. All right, so what are you going to start doing to this? You're going to start by factoring it, seeing if you can cross anything out. You're going to look at that denominator and see if there's any type of restrictions that's going on. All right, so I'm going to have x plus 2 in my numerator. If I factor that denominator, that's the difference of 2 squares. X plus 2, x minus 2. Okay, so right away, all right, I can take a look at this denominator. If I set everything equal to 0, I'm going to find some restrictions in my denominator. All right, setting that equal to 0, all right, x cannot be equal to -2, because if it was, that would make that a 0. That would make me having a 0 in the denominator, and I can't divide by 0. All right, little restrictions from here. X cannot equal 2, all right, because again, if x is 2, that becomes 0. I got a denominator of 0. That's going to be no good right there. All right, so right off the bat, all right, I know that it is discontinuous. All right, so it's discontinuous. All right, and then let's also qualify why here. It's because there are restrictions for the denominator. Okay, and then here again, let's go through and analyze just a little bit more what's going on here. All right, could any of these be some vertical asymptotes? All right, let's take this 2 right here. All right, if I take 2 and I plug it back into the numerator, I get 2 plus 2 is which 4. All right, so that right there tells me at x equals 2, I've got a vertical asymptote going on. All right, and so that's going to be what's causing that discontinuity. All right, now let's take a look at this negative 2. If I plug this negative 2 in, all right, negative 2 plus 2, that gives me a 0. All right, so this does not qualify as a vertical asymptote. All right, but here again, if I know I can't let x equals negative 2. If it's not a vertical asymptote, then something's got to be going on right there. All right, and it's going to end up being a hole. All right, now you want to prove that it's going to be a hole, or algebraically show that it's going to be a hole. Let's take that expression, all right, and then let's factor it. Let's factor it out, cross out, see what we've got here. I've already done the factoring, rather. All right, now can I cross out? Yes. Can I cross out? Yes. I've got a binomial x plus 2, binomial x plus 2. All right, I can cross that out. All right, as soon as I cross it out, I'm removing that x equals negative 2. So I'm making a removable discontinuity right there. Okay, so to sum up overall answer here, it would be discontinuous at, spell it right this time, there we go, discontinuous at, all right, couple different places, at my x equals negative 2, all right, and then we said I'm crossed it out there, so that makes it removable. And more specifically, we know that's going to be a hole. And then I also have one at that vertical asymptote at x equals 2. All right, because it's a vertical asymptote going on right there, then I know it's going to be a non-removable discontinuity. Well, there again, not doing a very good job on my spelling tonight. Okay, we get the idea. Non-removable. Okay. All right, now let's do one more before we draw to a close here. All right, let's take a look at a piecewise function. All right, a lot of times kids are going to want to just automatically do a sketch. I suppose there's nothing wrong with that. All right, however, if you can honestly think through what's going on in this piecewise function, all right, I think you're going to be better off. It's probably going to be quicker than you attempting to draw a sketch. Okay, I've got 2 pieces. This one is made up of 2 straight lines, so that one's going to be pretty simple. All right, my main focus here is at 1. What the heck's going on at 1? All right, well, at x equals 1, if I plug 1 in right there, all right, I'm going to have 2 times 1, 2 minus 1. It's going to give me an answer of 1. Okay, and I would have a closed dot right there. So at 1, 1, I would have a closed dot. All right, now on this portion of the graph, for x is less than 1, I would take 1, plug it in. 1 plus 2 is 3. All right, I'm at a different spot, and I would have an open dot. So at 1, 3, I would have an open dot. At 1, what did I say that was? 1, 1, all right, I would have a closed dot. All right, so picturing what's happening right there, you've got to have a jump in that graph. Okay, so for those that are not picturing this, okay, let's kind of do a really rough sketch here. All right, when I did this, for x is greater than or equal to 1, I plugged 1 in. 2 minus 1 is 1. All right, so at 1, 1. So at 1, 1, I know I have a closed dot. All right, and it's to the right of 1. Okay, this is 1 to the right of 1. All right, let's just guess rough slope here. I don't know, maybe something like that. All right, now let's do the second part of this. X is less than 1. Okay, so I plug 1 in. 1 plus 2 is going to give me 3. So at 1, 3, I've got an open dot because that's less than. All right, and then I want everything less than 1. This is a straight line. Let's do a really, really rough sketch. Let's say I know it's going to go through 2. So let's kind of something along those lines. Okay, but see how long that took me to do that sketch? Even though I was doing a really, really rough sketch. All right, it's a lot easier. All right, I plug in 1. I get 1, I plug in 1, I get 3. I know I've got to have a jump going on there. Well, if I've got a jump, then obviously I have a discontinuity. Alright, so I could conclude here that it is discontinuous at, and we know where it's at. It's right there at 1. So x equals 1. Alright, it is a non-removable because I've clearly shown that it is a jump. Alright, so it's non-removable. Much better job on spelling there. Okay. Alright, so just some examples of applying this concept of discontinuity and identifying it from looking at the functions, especially when you don't have a graphing calculator. How are you going to do this? What are you going to do? And how are you going to approach it? Okay, if you liked the video, go ahead and give me a like. And if you want some more help in math, go ahead and subscribe to my channel. Thanks.